So for instance, if we picked a couple, there is phosphorus, which is P, palladium, which is Pd, platinum, which is Pt, polonium, Po, lead, Pb. So a lot of them with P's. There's a bunch of T ones. There's thorium, thallium, thulium, tantalum, titanium, a lot of ones with similar words. The point being, use your table. If it asks, if a test or something or a quiz asks you to write a formula for a compound, and you think you know the symbol for it, that's great, but check. Because you may be not remembering it right. And there's no reason not to look it up. So look it up if you're not sure, because there's a lot of really similar ones. I'm going to grab a picture from the book here. Oh, except I forgot to load it up. Sorry, get it up here. So if you're following along, this is page 101. That's the picture we want. Okay, here's kind of a block of the periodic table. One thing, a couple words to know. The rows across the periodic table are called periods. So they are that's the name of the periodic table. Something that is periodic means that it does the same thing over and over again. So on that table, we have similar properties and positions as we kind of go across and then jump back again and then jump back again. We'll see how that works later. Because of that, because it is periodic, it means everything in a particular position on the table has some similar properties, some similarities. So everything in the first column is going to have some similarities. And so we call those a group or sometimes a family. And some of those have special names. The ones on the far left are called the alkali metals. The next ones over are the alkaline earth metals. And then you've got halogens and noble gases over on the right. The transition elements make this big gray block in the middle, sometimes called the transition metals. And there are, contrary to what the book says, there are some common names of the other ones. We're just not going to worry about them in this class. So the important ones are those two extremes and then the transition elements in the middle. You'll notice hydrogen at the very top left is kind of left out there. Hydrogen's a weird element. It's not really a metal, but it's in that metal spot. So with its electrons, it makes sense there. So there's some other people who have developed other periodic tables and put hydrogen in other places, but we usually just say, well, that's kind of a weird one, and keep it where it is. There is one other thing about the halogens. So you've got all 5 of them listed here, but technically, I would kind of put an X here. That very last one, or the very last 2 now, astatine and TS, I don't even know what that is. It just got named. But those are radioactive, and so they don't really have chemical properties the way the other ones do because they don't stick around, they decay radioactively. So we don't usually include them in the same category as the ones above them. But that's okay. Okay, so why group things in that way? Well, because they have somewhat similar properties. So the alkali metals, for instance, that first row, they all are metals. They're all shiny, metallic, and they all react in a kind of a similar way. I would do it for you as a demonstration, but it's too dangerous. So we're going to look at a video of it instead. One thing they all do is they all react pretty similarly with water. So I have the sound off here, but I'm going to turn the lights off and just talk about it. So this is what they look like. This looks like either sodium or lithium. They kind of get this dark coating on the outside because they react with air. They react with the water and air, and lithium reacts with nitrogen also. And then you can cut them. Notice they cut that with that knife there pretty smoothly. They kind of have a consistency of like butter almost, pretty soft for a metal. You can just cut right through it, and it exposes this nice shiny metallic face. Over time, as that face is left open, it will reoxidize, so it will form that coating again. And I wish it had some, like, telling us what these things were. So this must be sodium now. So that must have been lithium. This is now moving to sodium, which is even softer and easier to cut. I don't have any sound anyway. Okay, so here's them in water. So you put a little tiny chunk in water, and you'll notice it reacts pretty readily. Start zooming around, and it gives off hydrogen gas. Okay, put the next one in water. I think that was even a smaller piece. Same kind of thing. You see how it sort of zooms around and emits hydrogen gas? As you go down in the periodic table, they get more and more violent. So this is sodium now, zooming around, making hydrogen gas. Hydrogen gas is explosive, and there's a lot of heat created in this reaction. So if you use a large amount, you can actually cause a pretty good explosion. All right, so there was potassium, I assume. We don't have sound here. You can see that potassium kind of does the same thing, but much more explosively. Right, there's our next one, being even bigger, and then kind of shooting all over the place when it goes off. This is why we're not doing it here. It also, alkali metals react with carbon dioxide, so you can't use a standard fire extinguisher for them. You have to use a special fire extinguisher. Yeah, so you have to use a special fire extinguisher that's only meant for metals. It's called a Class D fire extinguisher, and it sprays powder all over the place. It's really messy. So the very last one, we missed it here, was cesium, which is the bottom one. And so you can see, again, a super tiny amount, basically does the same thing, but much more energy. So we're going to talk about a few things over the course of this chapter. One is this idea of groups, that chemicals in the same column kind of do similar things, but also what we call trends, which is like going down a column, more energy is released from these elements, or going across the periodic table, this thing happens. So we're going to see these trends also. If you go looking for this stuff yourself, note that there are a lot of fake videos on this. There is one that's really popular, this one, Alkali Metals. We should look at it just because, has anybody seen this or heard of this? So it's this UK TV show talking about, and he's basically talking about how you know, nobody ever gets to see these things really go in water, so they're going to do it. And they have all this, you know, this whole thing set up, how this is rubidium, and then they're going to do it with cesium. Let's see, you know, drops it in the bathtub, runs away. It's got a little carefully dissolving thing. And this was on TV, and they show it just like blowing up like crazy. Well, it turns out it's fake. Somebody tried to a chemist noticed that that doesn't quite seem like what it would do, and went to recreate it, and you know, didn't get it to work, and eventually got them to admit that, yeah, they just like put some dynamite in there and blew it up. So there are some fake ones around there. The other one was real that we looked at. So all right, so that's this idea of periodic trends and of families. So the alkaline earth metals right next to it also have some similar behavior, not quite as violent as the alkali metals, not quite as fun to watch. But as we go across the periodic table, you see that kind of similar behavior. So one of the things that we do when we look at the periodic table is we like to group things because it makes things easier to understand. If you know that all of the alkali metals do this thing, then you can choose what you want to do what you want for chemicals.
And so another grouping that we use is separating metals and nonmetals. So we'll grab another picture on the next page here.
So what we see here is the left side of the periodic table we call metals, and the right side we call nonmetals. And the ones right in the middle are kind of half and half. And the word for that is metalloids, or sometimes semi-metals. They're kind of half and half. So what do we mean by this?
Let's look at the difference between metals and nonmetals. So what are some properties of metals? What do metals do?
Do you know if something is a metal or not, if you see it? If you do something to it? Kind of nodding your head. So what are things that metals do? How do you know if something's a metal? What?
Conducts heat, yeah. So metals usually, we could say they have a low specific heat, which is actually not the exact same as thermal conductivity, but which is how they conduct heat, but you can say that it's similar for now. So they're going to transfer heat really well. What else do metals do? Or are? What? So they react, yeah. They rust, which actually the more defining version of that is that they're shiny. And then when they react, we see them become not shiny anymore, like when they rust or when they oxidize. And so metals are generally shiny, reflective. The official chemical geological term for that is luster. They have this kind of shininess to it. We can just say they're shiny. What else do metals do that other things don't? Ideas? What? They're magnetic. That is true for several metals, but not all of them. So it's not a general property of metal. That's most of the magnetic material that we deal with is iron, and so the fact that iron is magnetic is important, but a lot of the other metals are not. What else can metals do? Anything else? All right, well, one thing is metals conduct electricity. That's why we make wires out of them. So metals will pass an electric current with very little resistance. So they work well as wires. And then another property is that they are malleable. And that's an important property of metals that's different from nonmetals. What does that mean? Yeah, you can shape it, you can bend. So we got to be careful with that term, shape it, because you can shape lots of things by grinding them like wood or whatever. But malleability specifically means that you can spread it out thinly, or you can dent it without breaking it. So has anybody ever just taken a hammer and whacked the side of a car? Something you were mad at? No? Okay, that's probably good. But what happens if you whack the side of the car with a hammer? You put a big dent in the side, right? What happens if you whack a car window with a hammer? It shatters. Has anybody done that? You don't have to. Yeah, so a little different, right? So that's this idea of malleability. When you hit a metal, or when you smash it, or hammer it, or bend it, the atoms can rearrange themselves and form a new shape without breaking. And other materials, nonmetals, don't do that. And that has to do with the electrons. We'll talk about electrons later, but the electrons in metals can spread out and rearrange themselves, and the electrons in nonmetals are held tightly by their atoms. So when you cause that stress to a nonmetal, it just kind of falls apart. So it breaks, it shatters, it's brittle, that kind of thing. So we can list the properties of metals and just say the properties of nonmetals are the opposite. So nonmetals usually have higher specific heat. They're usually dull, are colored but not shiny. They do not conduct electricity generally. They're insulators. and they're brittle. They're not malleable. They fall apart, they break, they shatter, however you want to describe that. So that describes the two extremes of the periodic table. What about these green things in the middle? So what do you think would happen there? If you were to guess, if the metals conduct electricity really well and the non-metals conduct electricity really poorly, what do you think the metalloids do? Yes, it's not your question.
Somewhere in between.
Yeah, exactly. Thank you. It's somewhere in between. So the metalloids all have properties that are just kind of in between the two. They're kind of, in fact, have you heard this term semiconductor? That's like semi like part-weight conductors. So they're not good conductors like metals. They're not really bad conductors like non-metals. They're semiconductors. They're in the middle. They have in-between properties. So that's how we describe those metalloids. They have in-between properties for all of those things concerned. Sometimes they act more like metals, sometimes more like non-metals. To identify them, when you don't have a nice color-coded chart like this in front of you, they're all of the elements touching that black stair-step thing that you see on the periodic table, except for aluminum. How do we remember that aluminum doesn't fit that? Aluminum is a metal. Is that a hard one to remember? Not really, because we sort of know aluminum, right? So we know it's shiny, like aluminum foil. We know you can bend it. So just remember that aluminum actually fits in with the metals, and everything else goes with those semi-metals. Everything else on that stair step goes with the semi-metals. All right. Let's look at, with our last 5 minutes, let's just look at elements in the body. Because I think this is kind of interesting too. So here's a neat chart of the elements that you find in the human body. So you'll notice not everything is accounted for. In fact, most things aren't. These are, certainly you could find a lot of those other elements in your body, but they're not used as part of what makes your body work. They're not important. So the main ones are in red here, the major things that your body is made up of, which is carbon, nitrogen, oxygen, and hydrogen. That's what pretty much constructs all of you. Then you've got things that are minerals, that are not organic molecules, but mineral compounds that also are important in your body. So things like sodium and potassium that work your ions. Chloride is an important ionic compound in the blood. You've got plenty of phosphorus and sulfur and amino acids, proteins, things like that, as well as DNA. Calcium is used in bones, of course. Magnesium's in there as an ion as well. And then you have your microminerals in purple. So microminerals are some of the other ones that you need in your body, but only in tiny, 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 tiny amounts. And in fact, if you had too much, a lot of times you'd have some problems. So things like chromium, which is actually really poisonous and dangerous in some cases, you actually need a tiny amount in your body. Selenium is another one. Even arsenic, which we think of as poisonous, which it is, you actually need in trace amounts in your body. So that's what you'll find. That's what you'll find in the body. If you want to know all the specific percentages, there's a whole table on that in your book. You don't have to memorize any of that stuff, but it's good to know what's necessary in the body. So just as an example, you need about 3 milligrams of arsenic for a 60 kilogram adult. So that's a light adult, but still 3 milligrams is like almost nothing. 2 milligrams of selenium. So you don't need much of this stuff, of those trace elements. All right, let's stop there, but we'll get into atomic structure on Thursday. So lab today, we're doing energy and matter. We'll talk about that when we start up again. So we'll start at 2 normal time. So you got an extra 5 minutes if you haven't done your pre-lab yet. Finish that up. I'll go grab the labs from last week. I've got them graded for you.